Okay, off on to chapter 7, stuff like that. So, if you remember back to chapter 6, we were talking about sort of an introduction to organic chemistry. The first five chapters were really review, and so now 6 was a very basic introduction to organic reactions, and chapter 7 and beyond are going to be talking really more about the reactions themselves, and we're going to start about designing synthesis reactions with that. But first things first, right? So we've already talked about alkanes, right? So those are going to be the simplest hydrocarbons with just carbon-carbon single bonds. So now we're going to talk about alkenes, and so these have a double carbon-carbon double bond associated with them, right? So the industrial uses, there's a pretty amazing array of different chemicals that you can do, even with something as simple as ethylene, which is just a carbon-carbon double bond. That's it, just two carbons. You can go anywhere from methanol to acetic acid, acetaldehyde, to things like vinyl chloride, vinyl acetate, stuff like that for making polymers, right? So propylene glycol, you can come in here, right? So it actually has an extra methylene group hanging off of it. So there's a pretty amazing amount of different chemical processes that you can do about that. So, okay, so how are these made? They're actually made through what's called a cracking process, where you take these larger alkanes and heat them to very high temperatures, so in some cases 900 degrees Celsius, obviously in the absence of oxygen and in the presence of catalysts, and they start to break down. So the carbon-carbon bonds start to break, and so you get these hydrogen, so these carbon radicals here. So you get a one, from the two bonds, right? So the two bonds, one electron goes on one side, one electron goes on the other carbon, right? And then they can break down so that to make the ethylene and hydrogen gas. But basically, long strings of alkanes can be broken down into much smaller ones by heating them, obviously in the absence of oxygen. Okay, and so there's this term that we're going to be talking about this rest of the chapters, is what's called the degree of unsaturation. And so this is what this is saying is that really how many rings and double and triple bonds do you have in the molecule, right? So if we say that it's completely saturated, what that means is it's all single bonds, right? But if you add a ring, or if you add double bonds, triple bonds to it, we call that unsaturation. So you can get a good measure of how what the molecule looks like from the degree of unsaturation. Okay, each level of unsaturation leads to basically 2 fewer hydrogen atoms than if it was all completely single bonds, right? So like that. So when you link with a ring, when you link back up, right? So each one of the carbons where you link it are going to lose a hydrogen, right? When you make a double bond, right? So that each one of those carbons is going to have 1 fewer hydrogen on it, right? So it's sort of a count of how many hydrogen atoms you're getting rid of, okay? So here, right, ethylene has a carbon-carbon double bond, right? So it only has 4. It can only have 4 hydrogens to it. Ethane can have 6, right? So this is considered saturated. This is considered unsaturated. Okay, so now it gives some degree, but it's really you don't know like that. So because you don't know if it's a ring or a double bond, right? So a triple bond actually just counts as 2 double bonds. So like that. So if you take H6 or C6H10, right, it could be any one of these, right? So you can have, it's going to have 2 degrees of unsaturation. I know how you determine that, right? So you can have two double bonds, right? You can have a ring and a double bond, right? So that's 1 degree of unsaturation. That's another one, right? You can have 2 rings fused together, or you can have a triple bond, right? Because triple bonds sort of in this calculation is like 2 double bonds, right? So all of these, right, have 2 degrees of unsaturation associated with them, right? So like that. So how do you figure it? There is kind of a complicated sort of way. So halides and nitrogens can do this, right? So for every halide you have in there, that's removing a hydrogen. Nitrogens, stuff like that. So you can actually ignore the oxygen atoms. Okay, so you can go through this, right? Halides, and the book talks about this, but this is one of the few places where actually there's an equation that actually works pretty well, and it's actually this one. So degree of unsaturation it's actually two times the number of carbons plus 2 plus the number of nitrogens minus the number of overall halides minus the number of hydrogens. That number divided by 2. Okay, I'm actually going to give you this equation, just this equation, on exams and things like that. You're going to need to know how to use it. I'm not going to give you the key, right? But you're going to need to know how to use this thing. Okay, so like that. So so that's the formula, right? There's very few times in chemistry where you need to memorize the formula, but this is one of them, and this makes it much easier than trying to figure it out with that by hand, by scratch. So this hydrogen, right, or this halide here, right? So that could be fluorines, chlorines, bromines, iodines. It doesn't matter, right? If you have chlorines and bromines, right, you can lump them all together. Okay, so here you go. C6, H10, NBr, right? Okay, so DOU, right? So 2C plus 2 plus N minus X minus Br all divided by 2, right? So here we go. 2 times the number of carbons, so it's 6 plus 2, right? Plus the number, we have a nitrogen here, right? So it's plus 1. We also have a bromine, right? So that's a halide. Oop. Should be H. Minus the number of halides, 10. All divided by 2. Okay, so this is 12. 12 plus 14, 15. So it's 15 minus 11 divided by 2, right? So that would be 4 divided by 2. 2. All right, so that means, right, we have, right, so that means we have 2 degrees of unsaturation, so we can have, right, so we can have 2 double bonds, right, what's this one here, actually, right, so these guys had 2 degrees of unsaturation, so it could be any one of these sort of situations, right, so, okay, and so for this one, right, so C5H7 and O2, right? So DOU, 2 times 5, right? Plus 2, minus this nitrogen, right? Minus, there's no halides, and then there's minus 7 hydrogens, right? All divided by 2. Notice we didn't have to worry about the oxygens. That actually doesn't come into play here. Right? So 10, that's 12, minus 8 divided by 2, right? So 4 divided by 2. This is also 2. Oh, excuse me, 3. Why am I? Oh, here we go. 4. I hope I did my math correctly. There you go. 3. All right, so I forgot the 2. Don't forget the 2. That's a common mistake, obviously, because I just did it. But don't forget that 2. Okay? Something like that. So there you go. Okay, so an example of this one would be, right, so for this one, right, would be, right, this one would have a ring, right, and a double bond in it. Right, this one here, right, 3, so you'd have the ring, right, and then you'd have, so that's 1 degree of unsaturation, then you have a double bond here, so that's another degree, and then another degree right there. So there you go. So there you go. Okay, so naming, right? So we always talk about, naming. Okay, so this is actually can be a little bit simpler than what we've been doing before, right? So it's still going to be the exact same 4 steps that we've been dealing with the entire, for the alkanes. But instead, right, so you find the longest chain, but that longest chain has to contain that unsaturation point, right? So it has to contain the double bond, okay? And so to indicate that it's an alkene, right, so instead of A and E, we have the E and E double naming scheme, right? The way that we do the alkyl change just before, we have to include alkene, notice in quotes, we're not going to write it, but we're going to need to know it for the attachment points, right? So the alkene, right, that's why it's in quotes, right? But that, so as the, and I'll show you, stuff like that. So, but include this in your list of alkyl groups, because you're going to need to know where that where the alkene starts on the chain, right? Something like that. So the numbering starts in, with the smallest at the unsaturation, smallest number at the unsaturation points. Basically, what that means is it starts on the side and closest to the double bond. Okay, the numbering goes through the unsaturation point. So the number for the unsaturation is where the double bond starts, okay? And then construct the name as normal, okay? So with that, and include the number where the unsaturation part is, right in front of the. If you have if you have a hexene, right, you got to tell me where that the double bond is, right? So it'd be like if it starts at carbon 2, it'd be 2-hexene. Okay, so here we go. Okay. Here we go. Okay, so here's the here we go, right? So 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? So here we go. So here's the main chain, right? It has to include that double bond. Even if you can find a longer chain, right? We'll talk about this in a minute. Even if you can find a longer chain that's that doesn't have the alkene, right? So if this was a long group here, right, we'd have to include that double bond. We can't just take it like that. We have to include the double bond. Okay. So what do we have, right? So we have the right. So this is 1, 2, 3, 4, 5, 6, right? So it's C6. Right, so that would normally be hexane, right? But since we have a double bond, right, that becomes take off the suffix and hex to indicate that it has a double bond, so that's hexene. Okay, so that's our main chain, right? So what else do we have? Well, we have our alkene, right? We're gonna need to get the numbering for that, right? And then we have this methyl group, right? So then we also have this methyl group there. Okay, so. This side, right, so this side is closer, this end is closer to the double bond than this end, right, so the numbering is going to start like this, 1, 2, 3, 4, 5, 6, right, so the double bond starts at carbon 2, so, right, and then the methyl's at 3, right, so this would be, right, this is in quotes, we don't need to know, but we just needed to know that number, okay, so it becomes 3-methyl, 2-hexene. That's the name. Okay, so, right, so we have a main chain that's 6 long, right? 1, 2, 3, 4, 5, 6, right? And hey, we have a double bond in it. That's what the ene is. Where does that start? It starts at carbon 2, right? It starts at carbon 2. And then, oh, hey, we have a methyl group, right? Where is that hanging off? It's hanging off at carbon 3. Here we go. Okay, next one. Right? 2, 4, 6, 8, 9, right? There. Okay, so main chain, right? It's got to go through this, got to go through that double bond, right? So, here we go. Here we go. Now it's a little more focused. Okay, so here we go. Right, so here's the main chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Just so happen to be the horizontal. Okay? Now, we do have the alkene that we have to take care of, right? We need to number that, say where it starts, right? But then we also have these 3 methyls, right? Methyl, 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 methyl. Now, then, right? So if we started this end, right, it would probably give the lowest number set. But we need to start on this, on the left end, because of that double bond, right? So it has to be over here because the double bond's on this closer to the left side. Doesn't matter about anything else. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So the alkene starts at carbon 2, right? Right, and then it's 6, 7, 8. Oh, I forgot to number this, right? So this is right. So it's C9, right? So it's nonane. That would normally be nonane, right? But again, we'd remove the suffix to say it has a double bond in it, so that would be nonene. Okay. So here we go. So we have 6, 7, 8, trimethyl, right? 2, nonene, Okay, so we have right. So here's our name. Right, we have a main chain that's 9 long. Right. So we have a double bond. Where does it start? It starts at carbon 2. Right, goes from 2 to 3, and then we have 3 methyl groups. Right, 3 methyls. Right, we better have 3 numbers. Right, so we have a methyl group at 6, 7, and 8. There we go. Okay, now cyclic alkenes. Now there is a little bit of controversy on how you name these. Okay. Okay, so this is right. So this is going to be the main chain here, right? So it's 1, 2, 3, 4, 5, 6, right? So right. So C6, right? So right. Normally that'd be hexane, right? But what? It's a ring, right? So we have to put cyclo in front of it, right? But then it also has a double bond, right? So we need to get rid of that. So this would be cyclohexene. Okay, so that's our main. That is our main chain, right? Okay, so what else do we have, right? So we have we have to deal with that alkene, right? But then we also have to deal with this ethyl group here. Okay, so the question is, which one of these is carbon 1, right? So is it 1? So does it start here? 1, and it has to go through that double bond, right? It's 1, 2, 3, 4, 5, 6, right? Okay, if that's the case, then the alkene starts at 1 and this becomes 4, right? The other option would be to start this at 1 and then 1, 2, 3, 4, 5, 6, right? So that would be 1, 5, right? So if you went 1 to 2 right here, you can't go like this. You can't start here and go through. It's always where the alkene starts. So you assume that 2. If you're going to start here at 1, 2 is going to be right. You go through it, right? It's where it starts. So it's 1 to 2, right? So 5, 6, right? So these are going to be the numbers, right? So it'd be 4 ethyl, right? 1 cyclohexene. Now you could probably get away with not putting the 1 in there. I like to do it because it keeps up with the regular 4 steps. Okay. So that's naming, right? Hope I got that right. Yep. There we go. Okay, now one of the things that can happen is, right, so with double bonds, and you can build this with your model set. Is that double bonds can't rotate, right? So they can't free rotate like single bonds can. Okay, and so not only do they not do it on a model kit, right? They don't do it in nature as well. Okay, and so these groups here are actually frozen in 3-dimensional space. Okay, and so if you have 2 groups sitting on, right? So the other groups are hydrogens on this thing, right? So if there's 2 groups on there, right? So you can either do one of 2 things, right? So you can either look at the main groups. Oops. Right? Most people say, "Oh, look at them! Look at these big groups here," right? If they're pointing at the same side. The other thing you can do is just look at the hydrogens, right? So it doesn't matter which one you look at, right? So if they're both on the same side, right? It's cis, right? Just because like this one would be up, this one would be up, right? So it's cis. Okay. Now if you had this situation. Right? If you looked at the methyl groups or you looked at the hydrogens, doesn't matter. It's whatever easier for you, right? You can sort of think of this as up and this is down, right? So opposite sides. This trans. Okay, that's where they get the numbering from before, right? Cis and trans. They just recycle this. Now, if you have 3 on there, it doesn't work, right? Because this one's up, this one's down, that one's down, right? So do you pick these 2 or do you pick those 2? This one we wouldn't say that there's a cis or trans isomer of this. It just is. Okay, so if we're going to include this, right, so if we're going to name these things, okay, with the cis and trans in there, how do we do that? Well, it's the same thing. We just indicate, right, where the groups are coming off of, right? So here we go. Okay. Right, so you can draw in these hydrogens if it makes it easier. Okay, right, so our main chain has to include this double bond here, right? So we're just counting carbons, right? We don't care about that chlorine, right? So we just care about the carbons, right? So here we go. Okay, so there's the main chain, right? It's 1, 2, 3, 4, 5 long, right? So it's C5, right? So normally that would be pentane, right? But since we have a double bond in here, it becomes pentene, right? So now we need to indicate where, right? So now we're dealing with the side chains, right? So we have this right? So we're going to have to deal with the alkene. We need to say where that starts. I always put that in quotes, right? And then we also have the chlorine, which we would write chloro to indicate this is a side chain, and then the methyl. Okay, but this side, right? So the right side is closer, right end is closer than the left end to this double bond, so the numbering has to start here. 1, 2, 3, 4, 5, right? So the alkene starts at carbon 1, right? Along with the chloro. Chloro's there too. And then the methyl. Okay, now, notice how the hydrogens here and here, right? One's sticking up, one's sticking down, right? So that would make it trans. Okay, so you would just stick the trans out front, okay, and then label it as normal. Okay, so it would become, right, which comes first, chloromethyl. Chloro's alphabetically first. So it would be trans 1 chloro, right? 3 methyl, right? 1 pentene, right? So we have a main chain that's right. That's 5 long. Right? Oh hey, we have a double bond in it. Where is it? Where does it start? It starts at carbon 1, right? Oh, hey, and what configuration is that double bond in, right? It's in trans, right? So we have 1 hydrogen down, 1 hydrogen up. Okay. Oh, hey, we have a methyl group. Where's that hanging off of, right? It's hanging off of carbon 3. Right? We also have a chloro group, right? Where's that hanging off of? Carbon 1. There we go. So trans, 1 chloro, 3 methyl, 1 pentene. There we go. Now, the other thing is, the problem is, right, so that works if you have 2 groups. So what happens if you have more than 2 groups hanging off of there? Well, what they did is they decided to come up with this naming scheme, and actually uses the same priority rules as you learned in chapter 5 for dealing with the R and S, stuff like that. So, but we look at either side of that double bond independently. Okay, we're going to assign a higher and a lower, so it'd be like you would do like a 1 and a 2, but usually I just do high and low. Okay, now, if the high priority groups are on the same side, we call that the Z. It's actually German for, I'm not going to butcher the German, but it's German for together. The other way to think about it is it's on the same side, on this in your really bad German accent, right? If the higher priority is on the opposite sides, it's E, which actually means opposite. Now, this is a quirk of the German language, right? You would think that Z would be opposite and E would be on the same side, but it's not. This German is quirky, right? So that just so happened. Stuff like that. So you always have to remember it's on the same side, okay? In your really bad German accent, okay? Colonel Klink or whatever. Okay, so here we go. So again, if they're you look at the high groups, right? The highers are on opposite sides, so it's E. If they're on the same side, it's Z, right? So you look at this, you look on one side, see what happens. Then you look on the other side, see what happens, and then right, and then see, and then get your finger away and see what happens. Okay, so here we go. Right, so you're looking at this one, right? So C. I'm just gonna go ahead and draw this all out. right? So here we go. So we're going to start on this side, right? So we're going to compare, right, carbon versus chlorine, right? So, okay, chlorine's heavier than carbon, right? So this is going to be high, low, okay? Then you compare on this side, right? So you compare hydrogen versus carbon, right? So now, right, so this is what's directly bonded off of this, hanging off of this carbon, right? So carbon's heavier than hydrogen, right? So this is now high, and this is low, right? So then you open it up, right? So compare the highs, right? So one's up, right? So the high's up, high's down, right? So they're opposite, so that means it's the E isomer, right? So the highs are on opposite sides, so it's E. Okay, let's do the next one, right? It's reasons like this, right? So where you have a bunch of different carbons on, double bond in the middle, and you have a bunch of carbons off the here, that they needed to standardize this. Okay, beyond cis and trans. Okay, so let's look at this side, right? So, right, so we have carbon versus carbon, right? So it's a tie, right? So this has, right, 2 carbon-carbon bonds, right? 1, 2, right? Versus, and 2 carbon hydrogens, right? This one here, right, has 1 carbon-carbon, right? But it also has, right, this carbon-oxygen bond, right? 2 carbon hydrogens, right? So you compare carbon-carbon versus carbon-oxygen, right? The carbon-oxygen's heavier than the carbon-carbon, right? Because you're looking at the heaviest bond, right? So that makes this high and this low. Okay, even though it's longer, right? Right? So as soon as you find a difference, you stop. Okay. Now on this side, right? So this guy here, right? It has 1 carbon-carbon bond, right? And 3 carbon hydrogens, right? This one here, right? Because again, they have that and that, right? 2 carbon-carbon versus and 2 carbon hydrogens, right? Right. So this, you compare the carbon-carbon bond, right? So this has 2, this has 1, right? So this would be high, this would be low, right? Doesn't matter about the other side, right? So you compare these two, and compare these two, and then go away, right? So you got high on both on the same side, right? You can think of them both going down, right? So this would be the Z isomer. There you go. Okay, so stability of alkenes, right? So if you want, there is a way that you can interconvert these, right? So what you need to do is you actually need to be able to actually instantaneously form it into a double bond where it can rotate, okay? And so, right, so if you have here, right, so this one is actually going to be preferred, right? Because if you have the cis configuration, right, you have these methyl groups knocking into each other, right? But in the trans, right, they're pointed away, so you don't have to worry about that. Okay, so they actually usually they prefer the trans configuration because it's less steric strain, right? So relative stability of the alkenes, right? So it actually turns out, so reactivity of these, stuff like that. So tetrasubstituted, right? So you're right. So except for steric effects, right? So these are actually going to be more stable than these, right? You actually want carbon, a bunch of sp2, sp3s all in a line. Okay, stuff like that. So they like having this, particularly this single double, right? But also they like having singles right next to doubles. Okay, so the more that you get, the better things are. The more stable the alkene actually is, right? So alkenes at the very, very end of molecules are very unstable. Things that are inside the chain, in the middle of the chain, much more stable. Unstable, stable. Okay, so now be talking about reaction mechanisms. Okay, so this is actually going to be, right, so we already talked about this last chapter, right? So if you have, right, so okay, so remember when we said, oh yeah, it doesn't, this is actually away. When we said, oh hey, this doesn't, when you do this, it doesn't matter which side the H and the BR goes on there. It turns out, right, from here on out, it actually does make a difference. right? So you have this, right? So remember, right? This has negative character to it. The double bond has negative character. This has, so it's going to be attracted to this positive character of the hydrogen, right? Because of this polar bond. Okay, so this is going to attack there, right? Hydrogen can only have one bond, so it's got to get rid of these two, so it pushes them there, right? And so now it actually, you can actually predict which one, where the hydrogen is going to go. Okay, it turns out that this one, right? So the hydrogen is actually going to go here. Why? Because you want the double bond, right? Or excuse me, you want the positive charge, the on the carbon, which is called a carbocation, right? Positive charge on a carbon, intermediate. Okay. You want this charge of this carbon to have as many other carbons as possible, right? So here it would only be bonded to one carbon. This one here has three carbons bonded to it. So this is actually the preferred, what it actually prefers to do. Okay, so Br minus, right? This can come back and attack, right, to form this. That. Okay, or down. Doesn't actually matter. In this case, it doesn't matter because that's not chiral. Neither one of these is chiral. Okay, and so we're going to see this where it makes a difference on which side it goes to. Okay, so again, this is just a quick reminder on writing organic reactions. So there's a couple of different ways that we can do it, right? So your reactant is always going to be here, right? And we have two different ways that we can do it, right? So we can either add the second reactant, so we can this plus this, and then this is just supporting information. Or, right, so we can either do it like this, or you can write it, right, so CH3. Or we can put it above the arrow. Okay, so this, having it above the arrow, is the same as having it plus that. Okay, so plus, actually, I should have said plus BR, HBr, right? So that above the arrow is the same as a plus this, right? And then this is the supporting information down here, right? So solvent, temperature, things like that. But a plus this is the same as having it above the arrow. Okay, you also sometimes see if we have multiple steps, we'll do a 1 and a 2, right? And so that means you do the first one and then you do the second step. Okay, so the reagent that's important is going to be above the arrow. What's below, unless it's numbered like this, what's down below the arrow is going to be just supporting information. What solvent did you use? Temperature, catalyst, things like that. Okay, so you're really looking at if there's a plus something, that's definitely important, or it's above the arrow. Okay, so again, we talked about the orientation is going to make a difference, right? And so you really only get this one product out here, okay? And so it turns out that a Russian scientist called Markonikov worked on this, and what he found is that what we called it the more substituted. You can think of it as either one of two ways. You can either say it's the more substituted, right? So tertiary, right? So it has three. This one has 3 carbon-carbon bonds to it, right? So that's tertiary. Okay. You can also think of it as fewer H atoms hanging off of it. Okay. This one doesn't have any. This one has 2, right? So this one has 2, right? So it's going to go with the fewer. Students think of it either way. It's whatever is easier for you to see. Okay. So I learned it as more substituted, right? So tertiary is going to be. It's going to go in tertiary versus secondary versus primary, right? But you can also think of it as which side has fewer hydrogens on it, right? So this side had, right? So this side had 2 hydrogens. This carbon had 2 hydrogens. This had none, right? So the hydrogen is going to go on that side. Your Br is going to go on that side. Okay. Think of it either way. Okay, so but if both sides are equal. Right, so let's say these were both methyl groups, right? Then it's going to go in equal proportions. Okay, so like that. So you're going to get a 50-50 mix, right? So that side has one carbon, extra carbon hanging off it. This one has one carbon hanging off of it. They're both secondary, right? And so you're going to get a fairly equal mixture between the two. Okay. Well, so the question is why, right? And it all has to do with this carbocation intermediate here, right? So tertiary carbocation, right, where you have the plus charge, right? This carbon, right, has 3 carbons hanging off of it. It's going to be a lot more stable than this one here, which is primary, which only has 1 carbon to help it out. Okay, so again, it's like lifting a 100-pound weight, right? If it's just you and a friend, it's going to be heavy. But if you and 3 friends, it's going to be a lot easier. Okay? So you can think of it that way. Okay, so predict the product, right? So you're gonna get sick of these by the end of the course. Okay, so here we go. Right, so here we go. So there's a hydrogen, right? So see, notice I put it above the arrow, so that means it's the important one, right? So here we go. So you don't have to draw, if it's just predict the product, you just want the product, but sometimes it's easier to go in and draw the mechanism, right? So here we go. So there we go. Hydrogen's going to come on. So now the question is, which side does right? So which side do we want the hydrogen, right? Which side do we want the positive charge, right? So this carbon, right, has 1, 2, 3, right? So this side is the tertiary carbon. This one here only has 1, 2, right? 2 other two carbons hanging off of it, right? So this tertiary carbon is going to be able to be better at bearing the load of this plus charge, right? So that means the hydrogen goes here, right? Plus I minus. This attacks, right? So you end up with and again, you don't have to draw the hydrogens, but it's easier to see where things are going. So this is your product, right? Where the iodine goes, the double bond goes away, the iodine goes here, and then the hydrogen goes on the other side. Okay. Okay. So. Right. So the important part, right? You're adding water, and don't think of water as H2O. Think of it as HOH, right? And then you have an acid catalyst, right? So that's below. Okay, so this is what we're adding, right? So again, we're adding it, right? So it's just H plus something, right? So it's H, and then you're moving you're kicking that away, right? But again, you have to look at this carbon, right? So think of the carbons here. Right, so this guy there, right, it has 1, 2, 3 other carbons hanging off of it, attached to it, right, so it's tertiary. That one there, right, only has 1, 2, right, so the tertiary is able to bear the load of the positive charge, right, so it's getting, right, so it's getting the positive charge, right, while this side gets the H. Okay, plus OH minus. This comes back, attacks there. Oops. Like that. Again, you wouldn't have to show that hydrogen, but just to show you where things go. Okay, and so the positive charge goes here, and so the negative charge comes in and attacks it. Okay, there you go. Okay, so here's another question. So, right, so if I give you, not just predict the product, but what would you have to start with? Right, so, okay, so we're going to have to start with this, right? So we're trying to make only this product here, right? And so we have 2 ways, right? So we know we can add water, right, because we're adding HOH across the double bond, right? So with that little bit drop of acid in there, right? So we have 2 options, right? So we can either have the double bond there, right? Or we can have the double bond there, right? Okay, so what happens, right? So we can either have it here. Oops, get the colors right. There or there. Okay, and so let's say, right? So let's do the blue A. Right, this is the only product we want to make, right? Okay, so if we're going to put the double bond there, right, we have the HOH, right? So this comes into tax, right? Takes this off, right? So then we have to compare that carbon versus that carbon, right? So that carbon has 2 carbons hanging off it, right? So it has this one and that one. This one also has 2. So Markonikov says that if there's no difference between the 2, right, both products are formed, right? So in one half, it's going to go like this, and right, so where the positive charge is born there. So that means that's where the OH is going. And the other half, it's going to be, whoops, I'm sorry, backwards. The other half would be, right, the OH goes here, right, because that's where the positive charge is. The other half of the molecules, it goes there, okay? But for this one, right, but if it, let's do it here. Right, but if we put the double bond there, right, so now, right, so this comes into tax, right, so now, right, we would compare that carbon, right, so this carbon here only has 1, right, attached to it, so it's primary. This one has 2, right, 1, 2, right, 1, 2 attached to it, right, so this is going to be able to bear a lot better than this one here, so that means that's where the positive, that's where the OH would go, okay, right, so H would go here, OH would go here, and this would be the only product, right? So it's really this one that we're going to have to use. If we use the other version, right, we're going to get a mixture of products, right? Sometimes the OH goes there, sometimes it goes there. But if we use this product and this reaction, that's our only product that's formed. Okay, so carbocation stability, right? So we've been talking about this, right? So the more carbons you have hanging off of where the carbocation is, the more stable it is, right? So remember, 100-pound weight, right? So here, the methyl cation, right? It doesn't have any helpers, right? It doesn't have any of the carbons, right? So this carbon is bearing the full weight, right? So here, right, it has 1 carbon to help it out, right? This has 2 carbons to help it out. This one has 3, right? So it's going to be a lot easier for these guys to lift that weight compared to this one. So the more carbons you have hanging off of that carbocation, the happier it is. Okay, so Hammond's pouch. I'm only going to touch on this a little bit. We're not really going to delve into it. It's in the book, so we'll talk about it. Basically, what it's saying is that it's this idea of sometimes, sort of, can you predict the reaction, based on the curve, right? So this is actually a faster reaction, right, because it has a lower reaction rate, or it has a lower activation energy, right? But it gives the less stable product, right? But this one here, if you give it enough energy, it'll actually be able to get over that hill to get the better product, right? So if it has enough energy, right? So if you heat the reaction up, right, it'll be able to actually do this higher reaction to get here, which is really where it wants. But if you were to cool it down, it would at least get to here. So you can also think of, hey, if the reactant's transition states, right? So if the product is closer to the transition state, that means that the product is more closely resembles it. Here, the reactants, right? There's not much difference between those two, so that means the reactants must be closer to the transition state. Okay, so how do we know this mechanism is correct? Okay, and so we can predict structural shifts within reaction. Right, something like that. So we run this reaction, right? You would think, oh well, right. So the Cl goes here, and the H goes there, right? Right, which is what we see, right? But we also see this product, right, where it's adding actually not where the, not across that double bond, but next to it. Okay, and so this one, something's up with that hydrogen. Okay, and so what is it? Well, what can happen is, right, while this thing is sticking around, if you move this hydrogen here, okay, you can sort of see the blue hydrogen shifting over, okay, what you form is actually you go from a secondary carbocation to a tertiary. Right? So if there's a secondary, if there's an ability to make a secondary carbocation right next to it, you can actually shift the hydrogen, the hydride, over a hydrogen atom over to make that stabilizes the product, right? So the cost of moving, right, is more than made up to by this the added stability of the carbocation. And then since the positive charge is at this new spot, right, that's where the chlorine goes. Okay, you can also see this with alkyl shifts. Now this happens basically just with methyl groups. Same deal, right? So if we have a quaternary carbon here, right, so we can shift one of those methyl groups over. Same, it's basically no different than a hydrogen shift, right? But then you make a tertiary carbocation, which stabilizes the product, right? Okay, so how does this work? Okay, so how are you going to be able to predict it? Okay, so if I were to give this reaction and say, okay, draw the mechanism to show what happened, okay, so I'm not going to make you necessarily predict it, but you can tell something's up because the chlorine isn't adding where the double bond is, okay, and so here you go, okay, right, so normally you would say, oh, it should add, right, so you're adding HCl, right, right, a Cl should add here and an H should add here, but that's not what we're getting, right? What we're getting is the chlorine adding here, right? So what the heck happened? Okay, and so that's where this comes into play, right? So this comes into tax, kicks those over there, right, to form, right? And I'm going to draw these hydrogens, right? Right, and so here's the H that came there, right, and you're left with the, right, so H adds here, right, because it's primary. Cl, or the carbocation, is going to be left here. What happens is this hydrogen here, right, so okay, this one here shifts over to that. Okay, so you also add Cl minus, right, so you end up with this intermediate here, right there, and so you've gone from a secondary carbocation there to a tertiary carbocation there. Now this thing can come and attack to go there to make that. Okay, so that you get a hydride shift over to go from a secondary carbocation to a tertiary carbocation. Then while the right, so that stabilizes the molecule, and so the chlorine, right, eventually the chlorine will get attracted, the negative charge will get attracted to the positive to make your product. Okay, so last slide, right, so this chapter one of the things I want to talk about is natural products, right, so sirolimus, right, so, or it's also called rapamycin. It's actually, so you're going to see these, it was isolated from soil samples on Easter Island. Everybody knows Easter Island is because of the, I think it's the Moai, these giant statues. Okay, and so, right, so they, they get these things. They get them from coral. They get them from soil samples. They get them from all sorts of crazy stuff, plants and stuff like that, right? So like that, and so it turns out that it's an immunosuppressant, right? And so here's the structure, right? So all these double bonds. It's this huge ring here with this crazy stuff, and then that side chain hanging off it, right? So some bacteria came in and actually synthesized this thing, right? So it said all these stereochemistry, it said all these stereocenters, things like that, and it's actually sold by Pfizer as Rapamune, right? So if you have an organ transplant, right, you need to suppress your immune system so it doesn't start attacking your new liver or heart or whatever, stuff like that, and so you'll take this. It actually turns out that it's from 2010. There was actually a thing saying that it rescues learning from Alzheimer's models, but again, that's in mice, stuff like that. But I just wanted to show you what these things are, stuff like that. So these natural products are becoming more important, either for antibiotics or anti-cancer, immunotherapy, things like that. These complex things that we could, right? And so they're ways to start thinking about molecules, right? So you can test these molecules, right? So you can develop a screen. You can isolate these from soil samples and see do they do something, right? So do they hit your protein of interest, right? Something like that. So and sometimes you get a hit, and so from here you have a good starting point to build better molecules, something like that. So, okay, like that. So thank you.